Alright, what I'm going to try to accomplish in this video is to show you or demonstrate how we can apply the properties of exponents to the other properties of arithmetic and algebra that we should have learned prior to taking this course. Sometimes students who memorize all of the rules will have struggles with this particular kind of work because they cannot fall back on understanding of how numbers work. It's important to know both what the skills are and why those skills exist so we can identify when we misrepresent them. Anyway, another method to make sure that you know what you're doing is to try two different approaches. And we'll look at some of that here too. So for the first set of exercises, the goal here is to illustrate how we can apply the properties of exponents to other properties of multiplication. In this case, it would be the distributive property. The distributive property is required for success in all of these exercises. But what we're distributing is exponential in nature and therefore requires that we apply new rules as well. For example, to distribute x squared into this cubic polynomial, I simply multiply everything by x squared. In this case, I'm going to write it all out so you can see all the x squared got distributed literally into this expression. Now we apply the properties of exponents. If you multiply two numbers of the same base, you add the exponents. Now remember, this is x times x times x times x times x, which is x to the fifth. And then x times 2 times x, that's just 2x to the fourth. And x squared times 1 is x squared. Now, before I move on, I'll demonstrate that you can tell that these are correct by either A, substituting a value for x and putting it into the original expression, substituting that same value for x into your answer, and proving that you get the same results. If you have technology available, put the given expression into the calculator or Desmos, and you put your answer into the Desmos, and you should see only one graph superimposed on the other. That should be done for all of these, especially if you're not sure if you're doing the work right. You should definitely be checking, because if you're not, then you might be reinforcing this bad work over and over again. As you can see, if you keep making the same mistake over and over again, it's learning the wrong thing. Moving forward to part C, the only thing that makes this different is that our exponents happen to be fractions. But that doesn't change the properties. First, the distributive property, distribute the x to the 1/2, and then properties of exponents, starting with the product rule. Multiply two numbers when the bases are the same. Here the bases are the same, they're both x. Then you add the exponents. 1/2 plus 1/2 is 1. That is saying that the square root of x times the square root of x is just x, which is something that we've discovered in our work. Here, the square root of x to the 1/2 times x to the negative 1/2, multiply numbers with the same bases, add the exponents, or in other words, this is x square root of x divided by the square root of x, which is x to the 0, or just 1. And finally, part D, because it has the number, not finally, I'm sorry, but because part D has the number E in it, some people would get intimidated. Unless you're not a numberist, you can perceive that E is just like any other number. It's just a little special, but it's every other number. It's 2, 3, somewhere in between 2 and 3. When I distribute it, I get e to the x times e to the x, which is the same thing. I'm multiplying two numbers of the same basis, therefore I add the exponents, x plus x. And then here it's, well, these are not numbers of the same basis, so they cannot multiply or combine them in any way. 2 times e to the x is about as far as I can take that. Here, though, x plus x is 2x, so I've got my final result. And jumping ahead to h, again, what makes this difficult is there's some negative exponents here, but other than that, all the rest of the rules apply. For example, the distributive property and the product rule. To multiply two numbers of the same base, add the exponents. 2x plus negative x and negative x plus x, and that reduces to 5 to the x plus 1. Certainly a more desirable expression, 5 to the x plus 1, than the alternative that was given to us up in here. Moving ahead, looking at exercise 2, same principles as above, except this time we recognize it's binomials times binomials, or binomials squared, which reminds us that we have to use or apply the FOIL algorithm, first outside, inside, last. So demonstrating that here, we multiply the 2x, or 2 to the x, sorry, 2 to the x by 2 to the x. Then we take the 2 to the x times 3, then 1 times 2 to the x, and 1 times 3. So FOIL is FOIL. Doesn't matter what kind of numbers we're foiling, they all work the same. Now properties are the product rule here, no rule here, except probably order of operations. You must do exponents before you can multiply. So we keep the 3 and wait for later until we find out what x is. And then 2 to the x and 3. And here, this is an interesting point, we have 2 to the x's, and an additional 2 to the x, so that makes a total of 2 to the x's, and 3. So that's the final result there. Here, don't forget, this is where students are going to make the craziest mistake. They're used to just following rules. If they're used to following rules without understanding them, many students would just square 3 to the x and square -1 and call it a day. But this is really taking the binomial and multiplying it by itself, which requires, again, the use of the FOIL algorithm. First, outside, inside, last. No problems after that, as long as you know that you're supposed to FOIL the rest of it. Is very much exactly like part A. Finally, or not finally, I keep saying that, we get to part J, and what only makes this different is what we are foiling happens to be an expression with a variable in the denominator. That should not discourage us. We just have to FOIL it. First, outside, inside, last. So we have x times x, which is x squared, x times 2 over x, then 2 over x times x, and 2 over x times 2 over x. So each of these now has to be multiplied, and here we can see x divided by x is 1, so we just left with a 2. Same thing happens here, and then we have 2 times 2 over x times x, or 4 over x squared. 2 plus 2 is 4, so that's our final result. And for this set, finally for this set, we're going to look at 5 minus 2 to the negative x squared. And really, this is the same exact thing as here, because 2 to the negative x is really 1 over 2 to the x. So it's kind of going to look like this in the end. But anyway, keeping the exponent negative and foiling. Now remember, I learned when you square binomials, you square the first, you square the last, multiply the two terms together, and then double. That's a shortcut for foiling. So if you know that shortcut, apply it here. That's what I did. Save myself a step. And then 2 times 5 is 10, so I multiply those together, and 2 to the negative x squared is 2 to the negative 2x. Alright, for the next two exercises, we're going to be applying division, and what can we do with division of exponential terms? We'll just examine these three. First, 20 over a over 2 to the a. Now without instruction, I suspect most students would probably break 20 into 10 times 2 to the a, so that we could then apply power of a product. Power of a product enables me to take both 10 and 2 to the a power. Dividing that by 2a means I have two numbers divided that are the same, and I'm left with 10 to the a as a result. However, a more clever student might recognize that this is in fact an example of power of a quotient. That is to say, the power a is the same in the top and the bottom, which is really the same as taking the fraction to the a power. If you do that, then you can see 20 divided by 2 is a piece of cake. 20 divided by 2 is 10, and 10 to the a power is the result we're looking for. So power of a quotient, really handy rule, and usually we go one way. We go from the fraction to the separate exponents, but the power of a quotient is a property that works both ways, just like many of our numerical properties. 5 to the n plus 1 over 5 to the n. Looking at this one way, we can observe 5 to the n plus 1 is really 5 to the n plus 1 minus n. That is to say, if you divide two numbers of the same bases, you subtract the exponent. So this is the quotient rule, not power of a quotient, but the quotient rule, and then n minus n is 0, so we're left with 5 to the 1, or just 5. Somebody else might look at this and say, hey, you know what, that's the product rule again. This is actually 5 to the n times 5 to the 1. Divide that by 5 to the n, 5 to the n's divide out, and we're left with 5. So using the quotient rule, I get this result. Using the product rule and then using division, I get the same exact result. Similarly, 5 to the n plus 1 over 5 is going to be 5 to the n plus 1 minus 1, because this is 5 to the 1. Subtract the exponents, we're just left with 5 to the n. Or we could look at it as 5 to the n times 5 to the 1 over 5. 5's divide out, and we're left with 5 to the n. Where'd it go? There it is. So 5 to the n, no matter how you slice it, whichever order you follow, you should end up with the same results. All of these, of course, checked with technology. And second to last, what happens when you see division and there is a sum in the numerator? Answer, distributive property, just like before. If we're going to divide by 2 to the m, we're going to divide both the 6 to the m and the 2 to the m by 2 to the m. This then is just like the previous set of exercises. It becomes 6 over 2 to the m, which is just 3 to the m plus 1, because here, regardless of the value of m, we will always divide out to 1 because they're the same. Now, one could, and this is not something that I would expect, but this is a completely acceptable way to do this. You could take the number 6 and break it up into 3 times 2. Goal being that we have 3 different numbers with the base of 2. Having same bases makes work easier in mathematics. So that gives me, with power of a product, this expression in the numerator. Clever student might recognize 2 to the m as a common factor, which can be taken out, shown a good time. Divide that by 2 to the m. Divide the 2 to the m's, and we're left with 3 to the m plus 1. Same result as I had before, using a slightly different approach. Now for part D, it's actually a little bit tougher because what's in the denominator is actually binomial, not a monomial. So I can do the distributive thing, but I can't really go further. In other words, I could have 6 to the n over 1 plus 2 to the n, plus 12 to the n over 1 plus 2 to the n. No matter how I look at it, it's going to be a hot mess. So I'm instead going to try this approach right here, where I try to factor out the numerator so that maybe I can get something to divide out with the denominator. So 6 times 1 to the n, 6 times 2 to the n. My goal here, recognize that both 6 and 12 are powers of 6, and also now I can see a 1 and a 2 to the n up in here, so I'm liking the way this is headed. I'm going to use power of a product, and then I'm going to acknowledge 6 to the n and 6 to the n are common factors in the numerator. So I'm going to take out the 6 to the n, show it a good time, divide that by 1 over 2 to the n, and boosh, I get 6 to the n as a final result. This is a fascinating outcome. 6 to the n doesn't look anything like 6 to the n plus 12 to the n over 1 plus 2 to the n, but in fact they are the same. So hope that you find all of this helpful. Again, these are just basically nothing new in this entire video except applying 2 or 3 different rules in the right place at the right time. That's what makes math challenging for some. Once again, just as a reminder, if you try to understand these rules rather than just memorize them, you'll go a lot further with a lot less help. So anyway, thanks for watching. Have a good day.